Hi, and welcome to the tutorial on calculating numbers of atoms from moles and moles from number of atoms. And so we're going to start off with a couple of practice problems here. We've got how many atoms of calcium are in 2.45 moles of calcium, and then how many moles of calcium are in 8.58 times 10 to the 22nd calcium atoms. So in order to solve any mole problem, we need to think about the definition of the mole. And the definition of the mole is that 1 mole of any substance has Avogadro's number of particles in it, 6.02 times 10 to the 23rd. In this case, since we're asked to solve for number of atoms, and this is moles of an element, then this number is going to have the units of atoms. If I'm asked to count molecules, so like if this was a formula like H2O or something, then I would use the word molecules. So it's whatever the thing is that we're counting that we have Avogadro's number of. So 1 mole equals 6.02 times 10 to the 23rd atom. So if you start with that relationship, because those are the two things that I'm seeking to convert between, right? So how many atoms from this number of moles? So those are the two things I want to convert between. I think of what the relationship is between those two units, and then I go ahead and set up. So just like we solved any other conversions earlier in the year, we're going to start by putting, here's the number I was given. So I want 2.45 moles. Calcium. You don't have to write the calcium on there, but I just like to label things because that's what I do. And then we set up our conversion factor. So remember, a conversion factor is a fraction that contains two numbers that are equal to each other. So when I write down this relationship, I've got the numbers that I want to put in here. So the mole definition gives us the relationship between moles and atoms. There's always, for 1 mole, there's always this number of atoms, or for 1 mole, there's that number of molecules, etc. So then I just need to think about how to set this up. Same idea, we want the mole unit to cancel out, just like we talked about before. If I want that unit to cancel out, whatever goes on the bottom of my conversion factor should have a matching unit to this. So the original number from the problem out in front, and then these two numbers, one over the other, goes in here. So I'm going to put the 1 mole on the bottom, and I'm going to put Avogadro's number on top. If you think about it, if I'm trying to come up with a number of atoms, it's going to be a gigantic number, right? Because in any sample size, there's a whole huge, gigantic number of atoms, and so multiplying by Avogadro's number will give us a large number for our answer. So 2.45 times 6.02. So here's the deal. You can, for significant figures, whatever this original number has, that's what I want you to give me your final answer. So let's not factor in our conversion factor into that. So I get 1.4749 times 10 to the 24th. So this with 3 digits would be 1.47, and then don't forget the exponent part, times 10 to the 24th. And the units will be atoms. So there is a unit on every number that we write down. This number is no different. That unit should be atoms. Okay, so that's one type of calculation you may have to do. The second type of calculation you might have to do is exactly the reverse. So what if I am given a gigantic number of calcium atoms and I want to know how many moles would that be equivalent to? So again, I look at what are the units that I'm converting between. So I want moles as a unit, and I'm starting with atoms as a unit. So again, this relationship has those two units equivalent to each other. So 1 mole contains 6.02 times 10 to the 23rd atoms. So I'm going to, inside of my relationship defined, that I'm going to use, and I've put down the number that I was given in the problem. And writing down units will help you to make sure that you're multiplying and dividing by the right things from your conversion factor. So this is the number of atoms, gigantic number of atoms. So by writing that in my conversion factor, I'm picking from these two numbers, one on the top, one on the bottom. I want to end up with moles, so the 1 mole goes on the top. And then Avogadro's number, 6.02 times 10 to the 23rd, is going to go on the bottom, because that has the unit of atoms. So for those of you who still want to refuse to label units on things, Avogadro's number has the units of whatever it is that we're counting. So 6.02 times 10 to the 23rd atoms, that has that matching unit that I want to cancel. So this time, it's this number times 1, you don't have to put that in your calculator, but divided by Avogadro's number. So here's the thing. We talked about learning to use our calculator correctly, and if you still aren't using the buttons correctly, you're not going to get something in scientific notation that we're dividing by. It's not going to come out correctly. So what you should get is 0.14, again, keeping, this has 3 significant figures. I'm going to keep 3 over here, so 0, remember leading zeros don't count, 0.143, and the unit is now moles. So whatever I had up here, that's the unit that I have left over. So that is now the moles of calcium that are present. So let's look at our answers and see if they make sense. So for this first one, again, 1 mole contains this many atoms. So if I had 2.45 moles, doesn't it make sense that I've got more than 6.02 times 10 to the 23rd atoms? I have, in fact, 2.45 times this amount, and that's exactly what I did to find my answer. So make sure that even though these are gigantic numbers, that process should still kind of make sense in terms of what we're doing and why we're doing it. And again, I can get things in the right place. I should have canceled these out. I can get things in the right place by thinking about this conversion factor setup that we've talked about. The second problem, so 8.58 times 10 to the 22nd. Well, the base number is bigger than this Avogadro's number, but the exponent is smaller. So that means that this number of atoms is less than what I have in 1 mole. So notice that my answer comes out to be less than 1 mole, which should make sense to us. The other thing to notice is that the reason we work in terms of moles is that this is a much easier number to handle than dealing with these big, gigantic numbers of atoms. So when we go to do calculations down the line, although we're interested in counting particles, we usually count them in large groups in terms of moles to go on and do our remaining calculations. But we should be able to connect between the number of atoms, moles and the number of atoms. We need to figure that out.